So our review topic today is about drag forces, and we're first going to give a brief explanation of what a drag force is. Well, I mean, when something drags, obviously it's going to slow down. It's going to act in the opposite direction of how something moves. So if I have like an object moving, say, this way, maybe, okay. If I have an object moving this way, then a drag force is going to act this way. But a drag force is that sounds an awful lot like friction, but a drag force is different than friction because drag forces is proportional to velocity. In other words, if I was looking at it, if I was doing a graph of velocity and drag force, there's going to be some kind of positive relationship. It could be a relationship like this. It could be a relationship like that. But all I know for sure is that I'm not going to have what I normally have with friction, which would be a relationship like that. That it wouldn't matter what kind of speed I was going, I would get the same amount. That I'm not going to get from a drag force. So that can mean a lot of different things, but what it means for sure is that my force is not going to be constant. A lot of the things I could do with my old force diagrams where I just set all the forces equal, it just doesn't work as well when I'm using drag forces, and I have to use some differentials in order to solve that stuff. Okay. So we're going to do the simplest example, which is the example of the object that is falling. It's the easiest derivation to get an equation that comes up with velocity as a function of time. And that's what we're going to do here. So under derivation, we're going to look at coming up with velocity as a function of time. And the example we're going to look at is the classic. We have an object, it is moving, and usually we do it so it's falling. So it's going to be falling down through gravity. So there's going to be it's going to be falling down. If we look, it's going to have a downward force of mg and an upward force of drag force. And we're going to use a linear drag force for that proof. So we're going to say that F sub d equals minus BV. That's proportional, exactly proportional. So if we double the velocity, we double the amount of drag force. Notice again, we call it minus because it's going against the natural motion of it. And we're going to call mg positive. Normally when we do these force diagrams, we're always calling mg negative because it's downward, but it's the driving force. So we're going to use it that way. So if we look, so first thing we're going to do is we're going to use Newton's second law, F equals ma, and we're just going to say that the net force equals mg minus bv. Well, we know that the net force equals ma, and we know that a is the derivative of velocity as a function of time. And if we actually go through and look at these forces, this force is going to stay constant, mg. But you can see that this force here, the drag force, is going to start out really small because the velocity will be small. But it's eventually going to creep up. And as it gets bigger and bigger and bigger, it's eventually going to reach a point that it matches mg. At the point where it matches mg, where force or drag force equals mg, that's the fastest it's ever going to get. So the speed where that happens remember, that's the terminal velocity. In this case, it's going to be BV equals mg. So the terminal velocity is going to be mg over b. Remember, b is just some constant that describes it. The bigger it is, the bigger that constant is, the more force there is at a certain velocity. So, okay. So again, that's all we've got there. Okay. So next thing we're going to do is we're going to move some stuff around. So we're just move back to this. mg minus bv. Okay. And we're going to actually divide everything by b, because I want that velocity by itself. So I'm going to have m over b dv dt equals mg over b minus just v, because I divided that out. And I'm going to replace it with this constant here. So I'm going to call that vt minus v minus, sorry, not minus, do that. Okay. And I'm going to say that's just m over b dv dt equals all of that. Okay. I'm going to multiply it by -1 because I like doing that. I'm going to need to do that actually. So I'm going to have negative m over b dv dt equals v minus vt. I need that to make my integral a little easier to do. Okay. And then I'm going to actually do something really weird. I'm going to separate my variables. I'm going to put all my v things on one side and everything that's not a v thing on the other. So I'm going to actually disassemble this whole differential. And I'm going to say dv over v minus vt. So I'm taking this part here. Should I circle that instead? This part here and this part here, and I'm putting those together. And then everything that's left, this part on the bottom and this part over here, I'm moving to the other side. That leaves me with negative b over m dt. Well, I have these little differential things sticking out by themselves. The only thing I can do now is integrate. And again, I am going to treat this like this object fell from rest. So I'm going to call the initial velocity 0 and go to v, and call the initial time 0 and go to t. Okay. When I do that, the right-hand side has no terms at all that relate to anything. Those are both constants. So I'm just going to have negative bt over m. And the left-hand side, remember, is just going to be that, it's going to be the natural log. So it's going to be the ln of v minus vt evaluated from 0 to v. I plug all that stuff in, and I end up with, and then I use the quotient rule, I end up with the ln of v minus vt over negative vt equals negative bt over m. I take e of both sides, I collect terms, and I get that v equals vt 1 minus e to the negative bt over m. That's an important thing. Okay. And it's important for a couple of reasons. One, it doesn't matter what terminal velocity is. Well, you can solve for it with lots of different equations. It works. Okay. And it also doesn't matter what this constant is. It works in lots of different situations. So that's a bonus. Okay. It also matters because there's a relationship going here. If I did a graph of velocity versus time, I'm going to get a function that looks like this. And that's what a 1 minus e to the something graph looks like. And I'm going to end up with an asymptote that's going to be like this. And that asymptote is going to be that terminal velocity, because when this number reaches infinity, when it gets really, really big, that number is going to be 1 to the e to the negative something. It's going to be really close to 0. And then we're going to get just vt. And you should probably try taking the derivative of that. If you do, you'll get something along the lines of a equals g e to the negative bt over m. And you definitely might want to take the integral of this to come up with what the x is. That's actually a more complicated thing. So, but you want to try that to see what it's like. The example that I gave, the example I did was the one of falling in air. Okay. If you have something, say, falling through air, or which is a fluid like any other, okay, and they ask you stuff about it, you can actually figure a bunch of things out. So let's say you had that object falling through air, and they ask you, they say, well, what do the graphs look like of the motion? Again, actually, this would be kind of a good place to do that. X. Let's say if we want to find out what x sub t is for that object. Okay, so let's do that. So we've got we're going to basically integrate from 0 to t v sub t, which was, and I'm going to actually replace all these variables, which were what was it? This was the v sub t. So it was mg over b, and it was mg over b minus mg over b e to the negative bt over m dt. So I need to take the integral of that whole thing, this whole function. Okay. So I'm going to integrate the first thing, and I'm going to get mg over bt. And then I'm going to integrate the second one. Well, the integral of e to the u is just e to the u over u. So I'm going to have negative mg over b e to the negative bt over m. Okay. And it's going to be divided by negative b over m. Okay. But I want to point out that this is all evaluated from 0 to t, and we haven't done that yet. This is actually a question on last year's, the 2018 AP test. I graded it, and this was actually a place where a lot of people made an error, so I don't want you to do that. Okay. So for that one, it's going to be, so let's plug through all this stuff. So the first part is just going to be what it looks like. It's going to be mgt over b. Do 2 minuses, so it's going to be plus mg, there's a b, let's see, the b squared on the bottom. It's going to be m squared g e to the negative bt over m for b squared, and then minus, well, this part will just be 0. But this part actually gets to be more complicated because it's going to be minus m squared g over b squared. But it's going to be e to the 0, and that's just 1. So it's actually going to leave all this stuff intact exactly like that. So that's going to be the expression for that. Okay. I think that's all we have time for in the video, so we'll talk varying friction in class.